Welcome back. This is Xfixium, and welcome to the How to Make a Sega Master System Game Using Devkit SMS tutorial series number 16. In this tutorial, we go over using Emulicious to see how our code performs. We go over the tools Emulicious provides to view our graphics and memory data. We also go over bringing in the game logic in pieces to review how much processing it takes to execute each entity. Lastly, we go over some best practices when writing your code. Let's begin. Okay, so what I'm going to do here is we're going to actually compile and launch it through we're going to launch the game through Emulicious. And we're just going to go over the things that Emulicious gives us when we go to dev our game or to debug it and to check the performance of the game. So one of the first things I got to do is, since these cutscenes and the title screen haven't been done yet, it's gonna comment out the code using a control // and same thing for the title. And I think I need to also instantiate or to set the player variables. So we're going to use the reset player variables method within the setup here. So normally you wouldn't do this. This would be done on the title screen, but since it's not going to be done on the title screen, we have to declare it here. So, and something I wanted to go over that I didn't go over previously is, when it comes to this game, I am certain that all the variables that I'm going to use in the game are initialized. By default, when you use Emulicious, and it may also, I don't know if this is also how the Master System itself works, which it probably does. When you don't initialize a variable, it may be a random number that is put into the actual work RAM. So I know when my variables I'm using are being initialized, but you may not want to do it that way. So what I would do is, for these variables here, they're in a state that they're not initialized. So that means there is no value that's actually given by default for these values. So the unsigned cars and the signed cars and that, you can't just assume that they're going to be 0 when they are created in actual work RAM. And what you do to get around that is just have an equals, and then you would put whatever your value, your default value would be for that value. So it'd be equals 0. This is how we're saying now that the variable is initialized. So that's one way you may want to do it. And I didn't bring it up before because typically depending on the game, I either initialize it or I don't. But I wanted to bring it up. So if you're seeing some things that you're not exactly sure why it's happening that way, it's because it hasn't been initialized to a value. And I think by default, Emulicious, when you start up a game in Emulicious, it defaults as using randomized numbers or within whatever your actual work RAM values are. So, and you can turn that off, but I think it's best practice that you initialize your variables in some way, shape, or form. I do it throughout the game, that setup. I always say there's that load function, and then there's the update functions for the majority of the entities and other things that I use in the game. That is because during those things, I usually initialize the values that for those properties. So like, these properties up here, I would initialize a value to it somewhere, so it's always initialized beforehand before I use it. But again, and in here we have arrays that have been already initialized. We have anything that has an equals saying that we've already set a value to it ahead of time. So here, a lot of these arrays that I use are already initialized. This just some things are not pre-initialized, and some of them are just work, like they are values that get populated way before their use. So as long as you populate them before, or you initialize them before you use them, you shouldn't have a problem. A lot of these are initialized before I use any of them, but I just wanted to throw that out there, as that could be a issue that you run into, and something I didn't really think about while I was showing off the global source. So, and that would happen here if I would go to game and I didn't have the title screen to call reset player variables right off the bat. Most likely everything that has to do with players wouldn't initialize. So you know what, let's test that. So I'm gonna comment it out here. So this is without me initializing the variables. So, and what we're gonna do is we're gonna see if we can build this first of all. So let's do a compile bat, see if it builds. Okay, so it did. And again, we can look over these numbers here. So bank 0 is now 0. That means we used all of the allotted 15 or 16K or whatever it is by default. We used all of it that was allotted to us. And this is how much we have left in our source that we can put source code into. So we still have 11,000-ish bytes yet to write code for, so we still have pretty much left over here. And then our other banks outside of our source code banks, which is 0 and 1, is 2, 3, and 4. That's where we're keeping those banks, and you can see that under banks here we have those ones that were generated from assets to banks, so they're hanging out over here for our source code to reference. So those would be where our audio and our graphics are, and you can see that bank 4 still has about 7,200 bytes free to put more graphics or whatever you want into it. And when it comes to banks, you can create quite a few of them. So if you have a large project, you'll most likely have enough room to put all your resources in it. So okay, so it looked like it built. So let's do compile run. So here we're telling it to compile, and then we're going to run the game. So let's run it. You can see that the music's missing in the beginning, and the ghosts kind of just trail off. So obviously not what we want to happen. Looks like they're missing a bunch of logic, since it's probably most likely the player logic is randomized. So we're going to close this out. Boy, that was annoyingly loud. But okay, and then now we're going to come back over here to our game. Now we're going to initialize those variables. And we're going to build again. So I saved my changes, and I compile and run again, and we'll see where this gets us. We get music plays, and I'm actually able to play again. So there's a bit of a lesson to be said there. Okay, so now we know that it builds and it plays, and what we're going to look at is all the features that Emulicious has for us. It's quite a robust program. The individual who made it is very talented, very also dedicated to the program or the application. and they still update it quite frequently to this very day. So we'll go over some stuff. Some stuff I could not get to work for me, for the life of me. Usually I can get the debugger to work, which is pretty nice because you can actually step through your code. If you can make a breakpoint, and then when the code reaches your breakpoint, you'll be able to see whatever the values are at that point in time, making it convenient to debug. And again, we did that way back when we put in the extensions. You can see the Emulicious debugger extension was here, or is here still. And then what we would do is we would run and debug off of this menu. And one of the other things that I should detail is that when you go to use through our banks here, and we have the asset build, or either the compile or compile run, there is a argument here in SDCC where you can set it to debug. I don't remember what it is off the top of my head, but if you set it to debug, it will create another file. It's a symbols file for debugging. It's I don't remember the extension on top of it all. Most of it is explained under the extension on how to get it to work. So there's quite a lot of details here on how you would get it to work within a Windows environment and within the Visual Code too. So I'll tell you how to do it within Visual Code, and then how it works, and what you need to get it all set up. So it all comes down to first setting your batch file, or your compiler, I should say, in the end, because that's what the batch file is doing. It's going to be this command line here, and it's going to be your whatever the debugger syntax is. I'll create an additional file. You don't want to delete that file. You want to keep it, and then when you go to run your game, you're going to place that for the debugger to take advantage of it. And I'll show you what that looks like in Emulicious. Emulicious, there's a couple things you need to make sure is correct over there so you can use the debugger. For this game, I didn't use the debugger. It was kind of cut and dry and self-explanatory for the bugs that I had. So, and then sometimes I'll just make an array of test variables that I'll just take a look at in the workaround while I'm running Emulicious, and I'll show you what that looks like. And I'll just see if it's a certain value at a certain point, and I can just go through the debugger in Emulicious and step through things. So, if it's step through at a certain point, I'll know what those values are and then make the appropriate fix. And that's sort of what I did with this game for things that I didn't catch right away. So, but if you can get the debugger running, I would definitely suggest that more than inspecting RAM, because that's kind of a pain in the butt. So, okay, so after all that, we're going to, so I'm just going to run again, and I'm probably going to turn off the volume, because, or maybe not, it depends. So yeah, let me run it. So compile run. Let's hit pause, and this sound, I'm just going to mute sound for now. So this is Emulicious, and under the tools section, there's a whole bunch of options here. One of the things we're going to take a look at right now is the tile map viewer. Now I have this set up. You can have the view set up in different ways for this. You can have it that it's in a tabs kind of thing to take a look at this data, or you can turn that off and it'll give you this big old thing where it has everything combined in one window, which is nice. This is mostly how I use it, but what I'm going to do is I'm going to take it into the arrange tabbed. So I'm going to bring this back down. So we'll go over each piece and what it means exactly. So let's look at the first piece here, or the one that I want to look at. As you can see, this is supposed to represent our VRAM graphically. And I don't know if you can see this, but there's a double thick gray line that goes right through the center here. I don't know if that's coming up very well, but that is saying it's separating the two pieces of RAM. So remember when I said the first half RAM and the second half of RAM? That's exactly what we're seeing here. So we're seeing our first half of RAM, and we recall I said we're going to put all our graphics for the sprites in the first half of RAM. And another nifty feature that Emulicious gives us, since we're in tall sprite mode, we can actually arrange these tiles in tall sprite sequential order. So if I hit that, we can actually see the graphics that we have here. And then, as you can see, I make player 1, and you can see how tall this is. This is an 8 pixel wide by 16 pixel high graphic, and you can see that each part of these sections on tall sprite make up the entirety of a meta sprite. So each one of these are a sprite of pop, tall sprite, and they make up one meta sprite. So here, like I said before, we have the first 4 tiles that we're going to stream in the player's graphics, and then the second set of 4 is where player 2 is going to be streaming in. And since this is only a 1-player game, obviously this is empty. But you can see all the other graphics that we put into the game. It looks exactly the same as it does when we go over here to the meta sprites and we look at the sprites. It is, you know, our graphics here, and the entirety of our graphics that we put together is put into the first half of VRAM. You can see our cherries for the bonus, because in the first stage it's 2 cherries that come out. You can see all the ghost graphics. All this are sprites that we can use in the game, and we can also take a look at the sprites. So this is the sprites that are currently on the screen. So we have the 4 ghosts and we have the player, and if I hover over them, you can see in real time where they show up on the screen. So here's the first sprite of Blinky, and here's the second sprite of Blinky. These 2 sprites combined is Blinky's meta sprite. As I said before, meta sprites are just comprised of actual sprites. So we call each one of these sections a sprite, and the combination of many sprites and to create one entity is what we call a meta sprite. So we have one meta sprite here, but here we can see all the sprites that are being used in the game. And when we do that add meta sprite, and then we use Devkit SMS to do that, we add meta sprite. We can define our meta sprites as Devkit SMS allows us to do. And then that final call where I make that unsafe call to copy all the sprite data into the sprite attribute table, this is what happens at that point. Once it gets pushed to the VDP through its port and it gets to the VRAM, that's exactly how that's our fruit of our labor right there. So everything we did up to this point is what's being done here. So again, we'll go back to tiles. So tiles, and it's showing us it in a 8x16. And the way that we do that is if we go back to the source code to reference how this happened and what we used to get it there, we're going to go to our stage. We're going to go up to our set stage. So we're going to go to set stage, and this one of these is it. Probably set stage data, if I recall correctly. So we're going to go to set stage data here, and or is it up here? Sorry. One of these is it. Yeah, so it is this. So it's set stage data. So when we make that call, where it's getting loaded, you can see here, load sprite tile. So that sprite sheet that we defined here through assets to banks that created our bank, and we said we want to load in our sprite tiles data, the actual raw pixel data. And remember, we gave it an 8. So when this here is responsible for loading that data into here. So when we said 8, if I click here and we can look at the tile index, this is 8. So here it's telling you where these these tiles start at. So here at the top, it starts at 0, so that's where we started our player, and then second player was start at 4, and here the ghost data for our tiles start at 8, and all we said is, okay, take that whole sheet, load it in the VRAM at tile 8, and that's what it did. So here we got all our graphics pumped into here, and then the other side of that will go 8 to 8 times pixel size, because this is the background tiles. It doesn't follow that 8:16 rule, only the sprites do. Remember when we set our index to 256 to start our graphics? If you go back here and we go back to tile maps and we look at that first stage in tile map here, we set that offset to 256. So we wanted this tile set, which is this one. It looks familiar, doesn't it? It's exactly the same stuff that we put here is now over here, and we said that we wanted this to be in the second half of RAM. As you can see, the line goes across here, this gray line, and this is saying, okay, this is the second half of RAM. So we set it to start at 256, tile 256, and we select it. That's what that is. And you can see where we started at here. So this call from Devkit SMS is responsible for putting that graphic data into. So our tiles data that we had set up, that we exported, we said to do at tile 256, and then again we're using assets to banks global defined of the size of how many bytes we actually want it to be written into VRAM, and that's what happened here. So those two very useful or I should say 3 very useful defines when we use assets to banks. So it's going to give us our bank number, which is 3 in this case. It's going to give us our binary, a raw binary data, which is, it shows it as an array here, 3,168 bytes, and then we're going to get that size from assets to banks. So if we recompile again using assets to banks and we don't change the file name, anything that we make a change to here will automatically, dynamically get updated. So very useful. You just got to make sure you call the bank switch before you use it. Very, very useful. And you can see how that works. And this is, again, everything we've done up to this point. Now this is me showing it. So this is the first half RAM. We have 256 tiles total. 0 to 255 is 256 combined tiles that you can have. And for the second half of RAM, as you can see, and this is why I say things in rows, because I think of Emulicious. You can see the last 4 rows have this, looks like just garbage in here. This is actually where all that tile map data gets stored. This is where I think the sprite SATs, the sprite attribute tables towards the end here. If you have any sort of scrolling or other data, it all gets stored in this bottom half. So that's why we don't have the entirety of the second half of RAM to use, because our tile map lives in there, or a bunch of other data lives in this lower section. So this is really the last tile we can use. There's still some empty data here that you can maybe squeeze another tile into, and that's what Maxim is talking about in SMS Power when he goes into great detail about this data. Is like, if it is technically only 448 tiles total that you can use, but if you're not using certain features and there's some data here that just doesn't get populated, I think there's about 36 or 32 bytes, maybe 64 bytes of 32 or 64 bytes of data here that's just not used by the SAT, but it's within that general area. You might be able to squeeze a tile there, or if you're not going to use certain scrolling, like vertical scrolling, you could probably squeeze a bunch of tiles in there. And I do that in TeamNT in some portions. I just put tiles because some of the cutscenes I don't want to lose certain. I want to squeeze as much of it as possible, so I use every single tile possible. So with TeamNT, there are times when I have put the sprite down here, like for instance, one of the bigger cutscenes is where April gets rescued and she kisses one of the turtles on the head. That I had to use every possible tile for that to make it look good, and then I didn't have room for the heart. Well, the heart was only 4 tiles, and I wound up stuffing them down here because I'm not using the any sort of scrolling there, so I was able to get away with that. So there's certain things where I have used these extra tile indexes when I needed to. So, but for the most part, as you can see, we started at 2, 5, 6, and we put our graphics here. And then at 447 or 0 to 447, as you've probably been told over and over again, and that's actually 448 values total. So that's where that 448 tile maximum that Maxim himself has talked about. But you can get a little crafty depending to get it, squeeze a couple more tiles out of it or so. And then from here to here, so 256 to the 447, that's actually 192 total tiles. So that's why I keep bringing up 192. So our first half is in 256 tiles, and then technically the maximum, or I don't know if technically is really the word here. Normally you would have an additional 192 tiles to play with, which kind of is a bummer. It would be nice if we had the entirety of the 256 tiles that could potentially be used here to show more background tiles. But one of the things that the Sega Master System offers us is the ability to flip tiles up, down, or horizontally, and you don't have to be constrained by this. This is just how a typical game could work out. If you don't need as many sprites, you can definitely put your tiles up in first half RAM. The cool thing about the tile map is, remember, a tile ID on a tile is actually 9 bits, so it can go up to 512 easily. So that means you can put your background tiles from here to the very end, and that would be just fine. So you don't have to constrain yourself to just having your tiles here. You can have them up here, or you can maybe have the first half as your tiles. So it's very flexible in where you put your background tiles. It doesn't care where you put the background tiles, because it can always get to it through that short, or that 9-bit number that makes up the tile map. So you can put these pretty much anywhere you want. It's just the sprites that only have for its tile ID, it only has, or tile index, I know you want to look at it. It only has a byte to show it, so it can only go up to a maximum value of 255. And as you can see, if I click here, that's 255. So the only thing it can reference is up to a maximum of 255. So that's why in Devkit SMS you can say, okay, I want the sprites in the first half, or I can have the sprites in the second half if you need it to be, or if you want to play it that way. If your game doesn't have a lot of sprites, it might be better to put it in the second half, or if you need all that room, then you put it in the first half. So it's flexible in that case. So I think that's pretty much everything I wanted to show here for the tiles. And then we have the tile map. And I think what I want to do is reset it and then pause here. So remember that from the very get-go I've been talking about, okay, the width of the game is 32 tiles wide. So if we click on this, it says this is column 31. So 0 to 31 makes this the 32nd tile. So it's 32 tiles across. And you can see this line here. And we click down here, we could see that it's row 23, or 0 to 23 is 24 rows altogether. So again, I was showing that over here in SMS Tile Studio, and if I turn on the area grid and I invert here, you can see I have that same kind of box that goes around, and this is 32 by 24 if that's what the area grid is. So that 32 or 24 is this area grid, and our actual map, our stage, is actually bigger than the size of the viewport. So the viewport's this this here, as you can see, there's 4 more rows at the bottom. So the Master System actually has an additional 4 rows that are not in view when the game starts. So we actually have additional room there to write our rows. And as you can see, I write a row down here underneath the viewport ahead of time, and that's the code that I discussed up to this point. That's it showing it in action. So when this starts scrolling down, this portion will go down, and what our game does is draw a row just before it gets to it, and then you'll see the viewport will flip over at the top, and then I'd have to draw a new row up here as it's going down. And that was part of that logic that we created back in I think it was a common area. If you remember, I did a kind of I think it was this, yeah. So the get row was a very like minimal way to figure out where the viewport was going to go once it goes over that 28, because it only has a maximum of 28 rows in the view. Once it goes past 28, well, then it flips back to 0. So that's what we're doing here. We're going to look where it actually is when it's scrolling, and then we're going to get the correct row that we're going to use to call update row for. So, and that's why we have that as part of the calculation. Get row, so we know exactly what row it is, because it has a maximum of 28 rows, and then once it hits past that 28, then it flips back to 0, and then you have to account for that. So again, that's where all this comes into play. And I know it probably didn't really make much sense while I was going through it, but now we're going to see that in action at this point. So here it's at the very bottom. So in the beginning, we have it at the very top. So we can also see the offset here is the horizontal and vertical scroll. Again, Emulicious gives us all this data, which is very awesome. And you can see that our scroll Y, or vertical scroll, is at 0. So as you recall, in the beginning of the game, it starts at the top and then it starts slowly scrolling to the bottom, and we're gonna see that play out a little bit. So if you watch the screen and I unpause the game, it will start scrolling down, as you can see, and you can see the vertical scroll is now at 42, and we already looped the bottom of our view, and you can see it's going down, and the bottom of it already is at the top, and now as we're going along, we're going to update just ahead of the scroll. So we're going to keep on going and going and going, and that's how it looks like at that point in time. We're at the very bottom of our graphic, so we didn't update anything more because we're at our maximum. Remember, our maximum was 96. So vertical scroll is now at 96. That's our maximum. We can't update any more data because it's already, all of it's been updated at this point. So you can see how that works when it scrolls. It's very interesting, since it's not like we have all the memory in the world to make our graphics as big as we want it to, and it'll just automatically happen by the system. That's not how this works. You have a very finite amount of VRAM, and you gotta find ways to show more than just a screen's worth of information. So that's why there's the vertical scroll, and then there's ways to update a column or a row before the player scrolls into it, and that's like a huge part of creating any game for an 8-bit system. You could do it using vertical or horizontal scrolling, or if you want it to be a much easier experience for yourself, you can just load the screen that it's the size of the Master System's resolution, which is 32 columns across and 24 rows in height. So, and if you times that by 8 for each one of those, you're going to get 256 for horizontal, and for vertical 192 pixels. So that would be in pixel values. So again, I just want to show you that, how all that talk about updating a row and our viewport and how it actually plays within our game, this visually shows you how that is handled. And if we click on some of this stuff, we can look at the values. So the tile index is 307. If we go back to the map, this is that special tile that I said that would slow down ghosts when they get into it. And here, if we click on this one, we can see that's also 307. But here it also gives you the information of those flags that we discussed. Is it flip horizontally? Is it flip vertically? Is it using the background palette or the sprite palette? If it's 0, we're using background palette. If it's 1, we're using sprite palette. And then the priority, which is, will it be drawn over top of the sprites? Here it is true. If I click on this one, here it's telling me it's false. So it gives you all the information you possibly want. Anything you click on here, it will tell you the tile index that it is currently, so it's 307. And it'll tell you where that's located grid-wise, an 8x8 grid-wise, so row 11 in column 2. Again, this is very much how we've done things in SMS Tile Studio, and it'll also tell you what the hardware scrolling is. So the horizontal and vertical scroll, where that is currently, and here the maximum it can possibly go is 96, and that's the number that we talked about. If you recall, 96, that is the amount of tiles here times 8, and I think there's like 12 of them. So there's 12 tiles here that is bigger than the resolution of the Sega Master System, and we take 12 times 8, that's 96 pixels total, and that's what the hardware scrolling goes by pixels to give it that smooth effect. So here it's doing 96, that's a maximum. We're at the bottom. Hopefully all that made sense. And then again, there's always this section here where we have 4 rows that we can draw to. So if this went beyond 96, you know, it would keep going until about 255, then it'll loop back to 0, and we could still make graphics that's, you know, that'll update for much larger than just 96. And the same thing for the horizontal scroll. It can go much wider than something like a 96 or you know, whatever you decide to do, like say a game like Castlevania. So, and I hope that explained that. Sprites, tiles, tile map, and where we made that hardware scrolling is using, again, Devkit SMS. It has this set background scroll, and we give it this global that we increment depending on the amount that we want to. And this is usually based off of the speed of the player, so you'll see that it scrolls much faster when we have the pack boost enabled. So when the player, as we went over the player source, is in pack boost, its base speed is at 2 pixels per frame, and it goes much faster. And this needs to keep up with the player, so that's what it uses here. So, okay, I think that's all I need to show there. The last couple things that I want to show is the debugger. So with the debugger, we have quite a bit going on here. Here is where you can access different areas of memory. So we have the CPU, the ROM. This ROM is obviously our actual game data. RAM, which is our work RAM that we have all those variables for. So when we go back to globals and we talk about these variables here, those are that's what's set up in RAM at this point. So, and it should be sequential, I believe. So the first one, since we have any type 8, the first 8 across would be this, and then the second half would be of 8 would be this. So they're in bytes, so 8 bytes across, and this is what that represents. And it's in hexadecimal format, showing those values. So we have 1, 2, 3, 4, 5, 6, 8. I think I have them all here. I'll go usually by 16 across, or it does by default, I think. So here you can keep track of certain variables and watch them. So if you know, if something kind of is acting weird, you can take a look at it here and see what those values are in real time as the game is running. So that's something I use quite often. There's VRAM to show what's in VRAM currently. Again, that's very useful. But also the visual representation of it that Emulicious gives us, which is this, is also very useful too. So I don't use that as much per se, but I do definitely use the RAM section of this. And video RAM, then palettes. This is just those two palettes, the background palette and the sprite, and this is their own special bit of memory. So here we have 16 bytes, and again that coincides with SMS Tile Studio. If you look at it, this palette's 16 colors, and those are each a byte, and you see the output length is 16. So that's what we're putting in there as our palettes, and I can show you that real quick. So it gives us a visual representation of what we currently have in those two. The background colors, as you can see, is this color, and if you go back to this and we go to stage 1, you can see there's the red color, there's the pink color, there's our white colors, there's the 2 black colors, and then the green, and so on and so forth. So it's showing us what's currently in the background palette. And then if we go to our main sprite palette, then it's now showing us what the bottom sprite palette is. As you can see, it's a series of black colors, and then we get into this burgundy color, and then move on to black. So you can see those are loaded, and we can actually see that in hexadecimal format. Again, something that I typically don't really use this, but I mean, if you want to change a color, it will allow you to change things, to take a look at what it might look like as you're running the game real time. So all this can be actually manipulated to some degree if you want to do a little bit of testing in that department. VDP, I think these are just the registers that we're talking about. And again, we can take a look at what those register setups are. This I haven't really used this too much, so I can't really say too much, but that's because Devkit SMS pretty much handles all this. This is another thing under the hood that you are not exposed to. So when you set certain things in Devkit SMS, it has some properties, but behind the scene it's actually manipulating the VDP registers, which do a bunch of things that have to do with your current mode. If you're using zoomed in sprites or zoom sprites, it can be doubled up in pixels. There's a bunch of other, that when we talk about using tall sprites and all that sort of thing, I think that's also coming back to the register in this sense. So that's what these values are, and I really haven't gone over that stuff because it's a bit more technical and it's not really something you have to deal with directly. So in PSG, this is part of the audio. I don't know exactly sure what this is, so I'm not very well versed in the audio aspects of the Sega Master System. I imagine that these are some sort of registers, or maybe not, maybe something else. Don't take my word on that. So okay, so we went over all that, and here we have where you can make breakpoints in here within, because this is your game really. This is all the code that has been written for your game. And Emulicious takes the ROM and it decompiles it, and here you can actually take a look at that assembly code because it decompiles the assembly. That's really not too useful for us here because again we're in C world versus the assembly, but as you may dip your feet into assembly and maybe in the end just write assembly straight up, this would be very helpful. Again, you can break point on certain things here and then take a look at them and inspect them in real time to see what those values are. So, and then one of the biggest things I do use here is and we'll go into this next section. I guess this is a good segue into that. So we went through all this. I explained those details about as good as I can, I believe. And I'm going to close this out so we no longer need that. But now there's this event viewer. So this is the event viewer, and when it comes to seeing how much performance or how much processing power is being used, visually I look at this. There's also the CPU usage over here, which kind of goes hand in hand with this. This is when I want to see certain spikes of information and where that may have happened. You can kind of see that too. Not kind of, you can see that here, but this is a little more detailed as in what's creating those spikes. Like, is it VRAM write? Is it just a regular work RAM write? And I'm about to go over that to show you what that means exactly. So And I'll also go over this other feature, which is stepping through stuff. So I'm going to unpause this, and then I'm going to let it run, and then a pause. So I'm going to go to the previous frame here. And as you can see, you see all these little green dots all over the place, or squares. And you can see these bright green squares. If you hover over them, it tells you, first of all, let me explain the anatomy of this. So what is this exactly? What are you looking at? It's the screen, but then there's a whole bunch of extra stuff here. So remember we talked about the V-blank. So the V-blank happens right after the screen has been drawn. And you have to look at this in the way that a CRT monitor functions. So a CRT monitor, which is short for cathode ray tube, how it draws a screen is it starts at the very top left. So scan line 0, as this is called. And remember, I was talking about scan lines, and this is where we're actually going to go through that. So when there's a beam at the back of the TV, and we'll start at the very top here, and what it does is it will light up the phosphorus that's in front of the TV line by line, and it happens so quick that with our human eye we can't discern any sort of delay or any time that that it's not drawing to the screen. So it's super fast, and basically what it does is it'll draw from scanline 0, and it'll do it from left to right. And then once we get to the right, to where the very end of that screen where it's drawing, the gun will reset back to the left, and then it will draw the second scan line, which is scan line 1 in here because we started from 0. So it's going to draw that second scan line. It's going to draw it all the way across, and it's going to reset and keep doing this for every line until we get to a certain portion of the screen. Now, the Master System only cares about the 192 lines. So once it gets to the max resolution, vertical resolution, which is 192 pixels, as I just said, there's a moment that's called the V-blank. So you can see this RRQ, or there's an interrupt request. That's what RRQ means, where we're no longer drawing anything to the screen. I don't know if it's the true vertical blank, but I think vertical blank is where why we have an extra 4 rows. So this area here is where the true vertical blank is. But at this point here, we're not drawing anything. So we have it from here to the end, the last scan line, to draw or do things that are unsafe. So the last scan line is 261. If you check out the array, you can see at 261 is our last scan line, and where the screen is no longer being drawn is at 193. So we have from 193 to 261 to do unsafe code. Beyond that, once it gets to the end, we're going to start again at the very top. And this is, as you can see, the game is being drawn here. This is what we call the active display portion. So when we're doing things in active display versus not on active display, doing anything with the VDP as it's trying to draw things on the screen becomes slower at that point. So that's why when it's anything that's graphical that you want to get done, or if you want to do anything, well, basically anything that has to do with the VDP, anything you want to do with the VDP and you want to do it quickly, you're going to do unsafe. But you got to make sure that you only do it within this space, this allotted space. So the 193 to the bottom of this portion here. And what this means, usually when we get the vertical blank, what that means is to the TV, the CRT monitor, once it gets down and it gets done drawing the last of its scan line, it's going to go from the reset of that, whatever that last scan line is, and then it's going to go all the way back up to here, And that time that it takes for it to reset from here to here is what vertical blank is. So that small time that it has from when it gets done finishing one frame of the screen, and then when it resets from all the way down here at the very last one back up to the top, we call that vertical blank at this point. So that small amount of time, we're going to stuff some processing in there, and it's quite interesting. So that's what we have here. And on a NTSC formatted television screen, since I think it's 60 hertz or whatever it is, 60 frames or something toward that effect, you don't have as much time to play with it here because of how quickly it's being drawn to the screen versus like PAL, which I think is like 50 hertz or something of that nature. Again, I'm not a total expert at this, but it's actually, when you're doing it for PAL TVs, you actually have a lot more room to play with for that processing. But typically, depending on how you, and that's why I have two sets of times for the PAL one and for the NTSC, because there's also a difference in speed. So we talk about NTSC being 60 and PAL being 50. When we try and run a 60 or an NTSC timing video game within a PAL system, it will be slow. So everything will be slow. The music playing will be slower. The timings on the screen for everything will be slower. Everything will be slower when you would take a game that was written for NTSC timing and then you put it into a PAL formatted situation. So it would actually run slower overall because, again, it was meant to run for an NTSC. So there's a difference between those two regions when it comes to your timing. So now we have NTSC that does, I have those defines as timings, and for the PAL version, I would have to make those numbers a little quicker, so it would have the same timing if you put them side by side. When it comes to Pac-Man, you want it to have a certain feel to it. So, or Miss Pac-Man, I'm sorry. When you want Miss Pac-Man to have a certain feel to it, you want to keep that feel between both of those types of formats there. So that's why we made two different formats with the same defines, so we can later create a PAL version that feels exactly the same in speed as the NTSC, or at least try to get at as close as possible for that. So that's what that discussion is and how this all plays out. And if you see over here, we have the H blank. So the H blank is that time that when the gun in the back of the TV, when it lights up that first line, it gets to the end and it has to reset back to the beginning of the next scan line. That's what this little section here, as you can see, it has H blank, and it has a little bit over here too. So this allows you to do some things graphically off screen. Very, very small amount of time to do so, from what I understand. But this is how we got some effects for the Sega Master System that would normally not be achievable any other way. One that comes to mind right off the bat is the Sega Master System version of Sonic the Hedgehog. There's a stage in Sonic the Hedgehog that goes underwater, and half of the screen is a different color at points when you first enter it. So when the player enters the water, that palette color where the water is completely different than the colors outside of the water. And how they achieve that is they do some palette changes off of the H blank. So I'll change some palette entries off screen or off this H blank so that at a certain scan line, so wherever that scan line is for the water, it will at that point here start making the changes to the palette color so that it looks like we're getting more colors on the screen than what the Master System is actually capable of. And what we're doing is halfway, let's say like the water starts halfway, on the scan line that's halfway through the screen, it makes those changes to the palette on the fly. So the palette that happens on through these scan lines and then the palette that gets changed later is completely different. So it gives that effect that everything underwater is a different color because the water's blue, and makes those tones more fit into a something that would be underwater or submerged. So that's where some of those tricks get in play with. So that's why these portions are important. So, and we can see what's happening outside of our active display, and any little bit of time we can use outside the active display is going to be beneficial. So hopefully I explained that decently. I know it's not 100%. I am not a technical guru when it comes to this, but I have a general idea of how it works. So, and here, when it comes to the event viewer here, Emulicious gives us perfect picture of what that looks like. And if we would run this in PAL, we would see the difference here. It would be a lot more room down here to play with as well. It would update correctly, showing us the PAL timings that could be applied to this as well. So, but besides all that, what the heck are we looking at here? So the general idea is, and I do all my code that starts right after the VBlank, as I said before in the previous video. Once VBlank is achieved, I just start executing code right after it. So my code is probably a little different than probably what a standard way to do this is. My code starts right after this and it bleeds into the next frame. So I would say it's between frames really. And that's the reason why I use the previous frame here, because if I went to current, we wouldn't really have a good idea what's going on. If I go on the previous one, we can see what happened really. So I start executing code from line 193, which is where our VBlank starts, even though it says HBlank because I'm over here in HBlank. But that little purplish thing there is a special built-in interrupt request from the Sega Master System that Devkit SMS uses. And this is where now we go from active display into the portion that's waiting for the CRT gun to reset. So that's what this time is from here on down. This is where we can write our unsafe code. So as you've seen before, I try to write all my unsafe code as the very first thing that gets done here, and then I'll write all the other logic. So what this is the start of that code. So if we go back to our stage here and we go to our game engine, so here, run game, that's all this here is what's being displayed on that event viewer. As you may have known or have gone over it, the first thing that's going to be called into our code at first is our play audio. So because we waited for VBlank here on main, we played our audio. So our first look at this. So our first here, as you can see, these green dots going across. This is the code that pulls our input, and it's also the code that executes our audio. So that gets played per frame. Here, remember, pull audio. That's actually, I don't think this is it. I'm sorry. Exclude pull input. So it's right after VBlank. So he's going to play the audio. It's going to update the frame counter. So those first scan line or two will be here. And if we take a look at it, we can actually see where that starts, where it ends. So from 193 to 201, which is about 8 scan lines worth of processing, what we're doing there is playing the audio and updating the frame counter. So that's all that's happening there. So for 8-ish lines, yeah. So from 193 to about 201, I'm saying, is where we're doing that. And how do I know that? That's because when this green one comes into play, that means we're messing with the VRAM. And that's exactly what this is. Normal RAM writes, and this is VRAM writes, or when we're writing to a port. So then we go back to stage. And the way I know that is because unsafe SMS copy sprites to SAT. This is a function that specifically writes that sprite buffer data to the VDP. So, and we can test that. So if we go to our Emulicious and I close out of everything here, which I didn't want to close out of everything, and I come in here and I hit Control /. So now the only thing that we're doing is this. We're not doing anything else. We are loading the stage and all that other stuff, but that happens before we actually run the game. So now we're going to compile and run it. Again, we're going to go into the event viewer. Okay, now the game's running. Here we drew the sprites the first time around because we made that call to update ghost sprites because that's part of the load, but after the load. So here, as you can see, with only the main audio being played, and you can see I only left the unsafe SMS copy sprites to SAT. That's this bright green stuff going across the screen. As you can see, it takes, if I pause the game, we can see that it takes about 1, 2, 3, 4, 5, 6, about 10 scan lines to perform that for the amount of sprites that we have on the screen. So that's what that means exactly. Hold on one second. And then if I comment that out, this green portion, the bright green portion won't show. So if we close this out and I now take care of that, so that would normally draw all the sprites on the screen, but now that we don't have it, it shouldn't draw any sprites onto the screen. So if we compile and run again, as you can see, now the game is running, but now we don't see any of those bright green dots going across the screen anymore. It's because now we're not writing to the VRAM. We commented out the code that would do that, and as you can see, there's no sprites being drawn to the screen either. Again, we would need that to draw sprites, and as you can see, whatever it takes from 193 here to 203 is just running the game engine at this point. So I'm sure there's some other stuff that Devkit SMS does when it right after it gets done doing the IRQ. Maybe it doesn't, I don't know. But so for just running music essentially and updating a global variable and to run the update stage code, which would have to look through that switch statement, it takes roughly 10 scan lines to achieve that, which, I mean, 10 scan lines, and you have to think you have 261 of them to play with. So each time you use a scan line, that's pretty precious at that point. So we're using 10 scan lines to do basically, I mean, nothing at this point. I mean, other than the audio, really. So I mean, you can see how much this costs per scan line. We have 261 scan lines total, and you need to squeeze in performance for each one of these entities. It adds up. So here we'll keep adding things, and then I'll keep showing you how much it's going to take to run that entity in the game. So I'm going to close out. We're going to uncomment some stuff here. So initiate sprite, we showed out those things that have to do with getting the sprites to the screen, which does, this is the thing that does that. This is when we initialize the sprites, and then here we put those sprites out there. So what we're going to do is we're going to take a look at some other things. First of all, HUD update top. That won't happen unless we're at the very top of the screen where the score is. So we're not going to really see that in action. Update player tiles, we will see that in action. I'll show you. And again, update scroll, we won't be able to see that until we're actually scrolling up and down. So I'm going to leave those go, and I'll leave this update stage palette so I can show you some of that, what that looks like in our event viewer. So I'm going to comment out the rest of it. So again, we get to the bottom screen, and then the game starts running. And you can see there's something a little different here. We got more of this light green in here. And I'll go into explanation, except this time I am going to use the debugger to do so. So first of all, let me go to previous frame. I'm going to go to the debugger. So we have the debugger here. Typically the debugger, when you open it, will automatically freeze it, but I have it set that it doesn't do that by automatic. So here we can see the CPU usage, and this usually it coincides with what's showing here, to be honest. So if you put your cursor over it, it'll give you a number of what it's at currently. So what I'm going to do is I'm going to pause this. As you can see, pauses everything, and then if I go over top of this, we'll show you where on the grid it is, and then I'll give you the percentage of CPU is using at that point in time. So right now we're using 9% of the CPU at certain points of the processing. So this would be per frame. One frame was only using 6, then I was using 9 at that point, and then there's a point where I use 10% of the CPU up to 100, obviously. But then here's the real interesting part. So you can see now we have this thicker band of bright green, which is our VRAM. Again, we're going to start at 193, and then once we get to 201, as we had before, it'll do the sprite SAT copy over, but then it stays in this bright green for about it stays in there about, what, 9 scan lines total. And that is also the combination. So watch as here, this is a button that advances the frame. So we advance the frame one time. As you can see, there's nothing there anymore. That's because, and we keep hitting it, you can see it shows up and doesn't show up. Remember when I said that when we're streaming in the player tiles. So we're streaming in 128 bytes of graphical data to the VDP. And remember that code. So if I go to the player code here and we go back to it and update player tiles, this is it. Remember when we had our logic here that would alternate which visuals to update in the streaming. So we're only doing it every other frame for the player 1, and then on the opposite of this frame would be player 2. Since there's no second player playing in team mode, it's not necessary. So that's why we have this conditional here. If it's not here, it's looking if it is team play. Since that first conditional's false, we're not going to bother doing that copy over. And that bright green squares is the unsafe SMS VRAM mem copy. So that is what that represents on the event viewer. So since we don't have a second player that we're playing team mode, this only gets updated every other frame. So that's what shows up here. So we go back to our thing, and we can see that as we're clicking through, that only happens on certain frames. So every other frame. So that's what that shows. Now, if we were in team mode, this would constantly show every frame because the second player would also be updated in the odd or even frame. So that's what's happening here. And as you can see, we moved over 128 bytes or whatever, and that's pretty performant here. This is pretty small amount of price to pay for when it comes to the overall processing of the game to have that effect, and it brings so much more to the game. If it wasn't for this, I wouldn't be able to bring certain elements into the game as easily because I wouldn't have enough VRAM for the sprites to handle it. So this it's a bit of performance. There's a bit of processing you're going to lose, so you're going to have to process it regardless of what we're talking about. But because of it, I'm able to bring in markers for the ghosts. I'm able to have the full extent of graphics that go with the ghosts without trying to change or manipulate them into something else that would fit into the VRAM. It's a little bit of processing cost, but what you get out of it is overall a better gaming experience. And again, this doesn't affect any gameplay. This only affects the visual representation, and we can get away with doing the even odd in it because it only affects how quickly a frame can show for the next time around that it needs to update. So in this case, at least, the sacrifice you have to do for the processing portion of it, I think outweighs the con, which is you won't have an immediate frame of animation. You have to wait at least one frame, and most people, if not all, will not even notice that. They won't bat an eye at that sort of thing. It happens so quickly because you have to think there's 60 frames. Probably that 60 frames is per second at that point, so you're talking about a fraction of a second. It's really up to you if you want to do this sort of thing or not, but I think in certain scenarios is almost a requirement to do so, to bring a certain gaming experience for the player. So again, that's what it looks like when we're talking about scan lines. Before, remember I was talking about scan lines. They were using about 10-ish scan lines here to bring those graphics over here for the player, and that's what this represents. So, and again, we can step through and see. And there's another one I want to show real quick before we bounce out of here. CRAM. So CRAM is the color RAM that has to do with palette. Why are we seeing this here? What is this? This is within the stage when we go to wherever there it is. This is when we update the stage palette. As you notice, it doesn't happen every frame. So if we go over to it, remember we set a timer for it. So on the 32nd frame, it'll make a change. And then also on the 64th frame, it'll make a change. So that's why it doesn't happen every frame. But that little pinkish dot is where we make that call in Devkit SMS to change the palette. So here it changes the palette, and we might be able to see it here with the dots. So if I move on, we go over there, we made that call to the palette, and as that happened, the dots disappeared. So that's what we're doing here. And then when the next timer comes around, it'll bring them back, and that's what these are. So CRAM, when you see that, that means that we made some change to the palette, and we want to do that off screen. If we do an active display, wherever this happens, that's where you'll see those little dots show up on the screen, and it's kind of dirty. So you typically want to do this off screen. So, and that's why we're doing it off screen. As you remember, I put all the code that we wanted to have off screen or right after VBlank here. So essentially, when you see a little pink dot, that's exactly the end, pretty much the end of this code and where it ends. So you can get a good idea on what scan line it goes up to or how many scan lines it uses just to do this. So again, we'll look at it again, and so, and here where this happens is we go from 193 down to about 217. So it happens here, but there's some extra logic that's being applied here. So 217 takes us to that scan line. At that point, you can see here it's right at the end. So that's our last bit of processing. And this is what I use for litmus tests for everything. There are also profiles that profilers that Emulicious provides. I haven't used those, to be honest, so I'm not the greatest source of information for that. Again, I would have loved to show the aspects that are the debugger, and so you would need to use the remote debugger for this, and that section will be here, whatever extension that you decide to use. Since we're using the Visual Code extension, you would enable that to be able to communicate from this to your source code, and again, you'd go through the debugger over here in VS Code. So, and you can start it from there. It will launch this, and or it will at least hook up to this through the remote debugger, and that's how you would enable it. Or it is enabled, or maybe it is a checkbox or something. So you would enable it, and then you would pick your extension that for the code editor that you are using. Here we're using Visual Studio Code. So hopefully I explained that. So now we're just gonna piecemeal a couple more things in here, and just to go over some of that, and then I'll wrap it up and tell you when you should be worried and when you need to look to optimize your code, or maybe take things out of it that you may not want to get in. But there's other things you can do, like if, for instance, all the code will not fit in one frame. Typically, that's what you want to have it at, so that it's 60 frames, and that's an NTSC at least world, that you can fit all that processing, because you want to get all the processing done in one frame. If you don't get it done in one frame, it's going to bleed into the next frame, and when that happens, that's when lag occurs. So, or when the game becomes choppy. There's ways to avoid that. You can make it that it's 30 frames or it's 30 frames per second per se. Let's say that, so you can do a bunch of processing, wait for VBlank, do a bunch more processing, and then update the screen. That's another way you can do it, which would be kind of choppy. So you want to kind of avoid that if you can. So, all right, so we're gonna get out of this, and we're just gonna come out, and then I'm gonna add one of these one by one. First, I'll add the player, because that seems like something you'd want to do. So, and we'll take a look at that. Okay. So this beginning part is just a loading. As you can see, there's points where the entire screen just fills up. As you can see, now that I put a player on there, and when it's moving around, if I just pause for a second and I go in the previous frame, you can see now we've added quite a bit more processing to it. Just to have the player on the screen and do what it's doing is now bringing us down to line 247 just for the player alone. So we're talking from 193 to 247 for the most part. Actually, it might even be more than that, because I'm not on a frame where, of course, it would be nice to have a debugger for that. Okay, so then this is updating the player graphics in video RAM, and then the rest of the logic for the player, which goes up to 248. So from 193 to 248, just to handle the player logic and the unsafe logic that I was talking about. That's how much processing it's using for that, just for the player. So if I unpause, it will do things. And as I'm going around, you'll see it even increase a little bit more, because when I'm going over a dot, that's doing some more extra processing that wouldn't normally happen. So as we're going over, you can see the dots, the event viewers lighting up like a Christmas tree. When I hit the Energizer, you can see that there's even more processing. Will actually bleed into active display when I hit the Energizer. You can see that just a brief moment, and if I scroll up, that will even take more processing. As you can see, it's it's using quite a bit. Now we're showing the score, and every time I go over a pellet, it updates that score up there, and see how the event viewer is showing those events as I'm going over the pellets. So every time that happens, there's even more processing being used. So if we can, I can almost get there. I'm not quite. If I had the debugger on. So yeah, so here, now we're consuming a pellet. We're updating the screen. We're doing all these things here. As you can see, now it's starting to bleed into active display, and we can still look at that, whatever that maximum number is. So we're going to find our little purple thing here, and as you can see, to do everything at one shot for player one, to consume a pellet, to update the screen, to do all this business, we're bleeding into the active display at the 9th scan line. So I mean, we're not doing that much. And yet it's using all these scan lines to get the job done. So it's something to take in consideration here. I mean, maybe I'm simplifying it. Maybe this is more than I'm really saying it is. But I mean, for all the logic to happen, the update to the score and scrolling and all that other stuff, that adds more and more processing to it, and those things take up lots of scan lines by the time the end process happens. So again, I'll just watch this to see what happens, and if I see things bouncing all over the place, I know that I need to go back and maybe optimize the code. As you can see, when we're scrolling, a lot more processing happens. Not a lot, but it's enough, because you can see sometimes it bleeds into the active display, depending on. Here it bleeds into the active display because not only am I scrolling, but now I'm also updating the score at the top at the same time. So because that has to happen on the first blitz when it shows up here. Oh, actually that's kind of buggy there. Yeah, what the heck? I don't know what I did there. 0 right before I get to it. Or maybe it doesn't show up on the screen. Oh no, it does. How come I've never seen that before? This might be just a bug with this code that I put together here. So I'll take a look at that. Yeah. I'll have to take a look. But yeah, it doesn't update automatically. I wonder if that's always been the case. All right, so that's what we're looking for. So we see this event viewer. This is a Miss Pac-Man logic without really anything else added to it. No scrolling or whatever. But once you add the scrolling, we're updating the score. It becomes a little more intensive. So, and then we go through. We're done with the stage and we move on. So again, part of that whole logic, but you can see for sure while we're going through this that it takes quite a lot of processing just for one player to do to play through. So, and we could probably get some more performance squeeze out of it. And the one compiler thing that I use is, and it doesn't yeah, for some reason there are some differences here from this and the base game that I have put together. It looks like there might be a missing pixel separation, but I'm not sure. But whatever, that's neither here nor there at this point. So I'll give you somewhat of a reality of what it takes to process something as simple as this within the master system. So again, you can. What I'll do is I'll watch, and if I see it go over something that I'm not comfortable with, I'll go in and retool the code to some degree, and to fix that issue. So, and then we'll start adding each ghost in piecemeal. So I'm pretty sure something else here isn't happening or something. So I'll uncomment out this other bottom code stuff, and then we're just going to bring in Blinky, only Blinky into the stage, and we'll see further how that affects our processing and how much processing it takes to do that, to bring in one ghost and one player. As you can see, now our active display has quite a lot of events going on for it, and you can see that Blinky's doing the chase thing. And his behavior is to always target the player. And then you can see he switched directions there, and now he's going off doing his own thing, because that's because of the scatter behavior. The timer reached the scatter behavior, now it's going to now go to the chase behavior, and this is the last one. And Blink is going to come after us the entire time, following us through the screen. But again, you can see through the event viewer how much that takes for that to happen. So you have Blinky in there, and it adds quite a bit. You see when he's in the house, it isn't as much processing at that point because we're doing no collision detection, and we're doing very few things at that point. So, okay. Again, bleeding into the active display. And then what we're going to do is I'm going to rip the band-aid off, and I'm going to put all the rest of our ghost entities, all the rest of entities that the game's going to have, which is our bonus and our ghost entities. So Pinky's logic when chasing the player is very simple. It just gets whatever the tile index is for the player at that point. But the other ones are more complex. So Pinky, like I said, follows the player four tiles in front of the player, and Inky needs Blinky as part of his coordinate system to flank the player, and then Sue, which when Sue gets close enough to the player, it will retreat. And maybe I'll show some of that. So like for Sue, and it's going to take a bit for her to show up at first because she's on the timer on stage 1. So we'll be waiting around just a little bit. But we also get to see the bonus play in here. So when we reach 70 pellets, the bonus will make its way through here. So while we're waiting for Sue to come out. This is really slow. I'm used to playing it with the turbo on. So here comes Sue. So if Sue's within a certain area, it'll just retreat to the bottom corner. Once it gets close to the player again, it'll retreat. As you see, the bonuses making its way through. I'll eat that. And Sue's default behavior is once it's in chase mode, it goes after the player, it'll retreat to this bottom left corner. So here it's trying to get to the player. It's a little too close, so then it decides to retreat. So it'll never actually hit the player. It will always retreat towards that bottom left corner when it gets too close to the player. And that's some of the logic that we did when we put this game together. So, and then if you force the issue and you're too close to the corner, here it's just going to spin over and over again because it's too close, and now you're also, it's already trying to get to his target tile to the bottom left. So that behavior is part of the Pac-Man ghost behavior. So again, Sue never really goes after you because again it's supposed to be a bashful or shy ghost. So there, we're showing that behavior based off the logic we have written. Like I said, Blinky comes straight at you. Pinky is essentially Blinky, but it's 4 tiles in front of the whatever the player's facing, so that's kind of boring. And then Inky's more is the one that does the flanking, so maybe we can see some of that in action. So we'll use those 2. Again, we want to keep track of this event over here. And as you can see, the ghosts don't seem to take all that much processing for both of them. And by default in scatter mode, Inky goes in this corner as if we went over. It's hard-coded to go to this corner in scatter mode, just like Sue's hard-coded to go in this corner during the scatter mode. So remember that tile, the target tile is down here. This one's for Sue and this one's for Inky, sorry. Blinky can pick either it doesn't matter which one for Blinky. It will pick a random one out of the 4 to go to when it's in scatter mode. So right now we're in scatter mode, and then as this goes around, you can see chase mode will ensue. Yep, there we go. We changed direction now. They're going to go tiles that are associated with what I set. So you see Inky's trying to come around on the other side to hit me, whereas Blinky was coming straight at me. So we'll see that again on the chase when it comes to play. So it's just using wherever Blinky is, it's trying to get the opposite of it to do a flank. And I guess I could show that with test tile, but that's how I originally made sure that made sure that the behavior was correct, is I had these test tiles that would show the targets that they were going to. That's why I had that green and red tile at the end of the tile set, is so I could see that in action and make sure that behavior was in fact correct. So I don't know if that really showed anything, but hopefully it did show something. That's weird. Got a little cut off there. So, and then let's put all the ghosts in, and we can see just how much that takes up for processing power, because that's really what we're here for. I'm going to compile and run once again. Now we have them all run. As you can see over in the event viewer, it's going pretty much nuts. And we look at our last scan line, because remember we bleed over into the next one. So we're at 193 is where the vertical blank happens here. So we're using now 106 of our active display, and you have to remember it's 192 total. So if we're using 106, we only have, we have less than 90 scan lines to use for processing. And as you remember or recall, just having one player on the screen used a very large chunk of processing. So if you would have it in team mode, it would definitely become tighter at that point. So again, that processing flag really helps here, because now when the ghost is looking for a target, and we're only looking for a target for only one ghost per frame, so it really helps cut down on some of the, if I would do the processing over and over and over again if I do the processing all at once for targeting for all 4 ghosts, it would be pretty hefty at that point. So it would still be doable, but it would be that our processing would be probably closer to like a 160 scan line instead. So it helps. Any scan line that you can get back is good for the game overall. So as you can see, this is even the maximum of processing, because we're not even scrolling yet, and we're not updating the score. So if I go to the top of the screen while scrolling, I'm sure that would be even more processing power. So if we take a look keep our eye on that event viewer as we're going up, you can see it increases substantially. So, and then when the ghosts are in frightened mode, and as you can see when I'm pausing the game for a little bit, that processing becomes much minimal at that point. Again, I'm scrolling and updating the screen. Scrolling doesn't take that much, but especially again using that unsafe method, that helps so much. Oh, I'm screwed. So yeah, and I think probably a good idea is also to show you what it looks like with let's see, it's game mode. Let's try team play game, even though I can't move, and we can really get a good idea what this thing looks like if it works. I don't know if there's any more additional setup I need to do that normally the title screen would have done for me. I don't recall. So, and we'll see how that looks when you have 2 players updating the score in memory. So Let's take a look. All right. Actually, it's not as horrible as I thought it was going to be. That's probably the reason why it doesn't lag on me. But you can see it was at 106 or 103. Oh, now we're at 130, adding the other player onto the screen here. So, again, it's not too bad, really. I thought it was going to be worse. I don't remember what it was. And this is without setting the optimized flag, too. So, it looks like player 2 is going to get chomped. Unfortunately, that is the case. So, and when they're not chomping pellets, it's not as bad, but once the bonus comes in here, that's when everything starts chugging along for. So, I mean, if we look at it now with the bonus and everything on the screen, which is a good test, stress test to make sure that, I mean, we could do scrolling as well. Again, that's not going to add too much to everything. So if we take a look at the number now and we go down to where the 193 is, we can see now we're at 150-ish. And again, we have 92 scan lines to play with. So this is comfortable, to be honest. So, and then we take a look at the debugger, which I guess I have to play some game here. You can see how high we are now. We're at like 95. So we're really getting to the point where we're stressing this out to the max. So this is the one I really pay attention to, but obviously this is a good visual representation of everything. But I know that if we would keep on having processing that would go beyond one, so if you would keep processing past 192 into 193, once that happens, the game will lag or slow down dramatically. And if you ever played an 8-bit game when there's a lot of things going on the screen, and it starts slowing down, that's the reason why. Is because all the work that needed to be done or all the logic that needed to be processed within that one frame, there wasn't enough time to do it for that certain scenario. So everything slows down, and until you get rid of some of the entities on here. As you can see, as I added a new entity and added more processing, and I added another second player, I added more processing. So when you have less entities that you have to calculate on the screen, you're going to then need less processing, and then you won't bleed into your next frame. But that's the whole idea, is to get all your processing done in one frame before the next frame comes around. You want a nice comfortable buffer between your last scan line of processing and then when you go into VBlank again. So at least with this scenario, and I hope that made sense. So, and this is very important because, you know, you'll get a real feel where you need to get creative with your optimization, like I had to, and yet still provide a good gaming experience for the player. So, and that's really what we want out of this whole thing. When I did a one player for this, I knew I wanted to have it as team play as well, since the original Sega Master System did offer this. They offer some different variants of it that I'm not, I don't really care for that much. I don't like the idea of bumping into a player in cooperative and then getting sent flying across the stage. That's something I personally don't really care for. But I mean, you know, we could actually add those sort of things to this game. There's still plenty of processing power to do it. And then, of course, I compared this game processing-wise to the Master System official release, and they're definitely streaming a lot more tiles than I am, and I think it also feels that way too. You can definitely tell, it seems, even though when there's pack boost and all that sort of thing, it doesn't seem like it's a very fast game for whatever reason. And it uses, there's times when there's lag and slowdown, so you can definitely play that game. And when you play team play mode, which is my stress test for this type of game, the original one does slow down quite a bit. It even tries to compensate for it by moving one of the ghosts off screen so it doesn't have to be processed anymore. I've noticed it has that behavior to it. So it's very interesting how things are how you develop certain things or certain behaviors to counteract certain things, because even the original one that was made, they had to kind of cut some corners there on the team play. So it was very interesting to see that behavior and to look at the event viewer and see how much they're doing. Out of the two, this one actually does less processing, and I don't think I've run into any major lag with this version of it that I've created. So I think that's everything that I want to go over for this particular video. Hopefully it's informative. I know probably there's some things here that are not correct all the way through. I consider myself more of a an intermediate level developer for this, so not everything that I say here is gospel, and it's not everything here that I say here is not like, I don't have years of experience behind it. So I have some experience, but not like your true masters that are out there that, you know, they dev this in assembly, you know what I mean? And they know the ins and outs of it. So, and there's plenty of those people on SMS Power that have more in-depth knowledge of this, and, you know, and there's just like I said, there's some true masters in there that have created some great games, you know, and some of those games I was able to get a hold of. There's this, I guess, a French website where they sell these games. So, you know, I have a couple of like Baru, and what's the other one I have? I think it's Heroes versus Demons or Against Demons. That one's that's amazing. There's these what was it, Bruce Lee game that was made that was visually just amazing looking game, and there's just a lot of great talent out there, really. I hate, the thing is, I hate to pronounce your names because I know I'm gonna get them wrong. The only one I really know is Ichigo Bankai. I know that one because Bleach, but they do some very, very good work. I mean, top tier stuff. So just a lot of good names. And then of course there's, like I said, Maxim. Those people are definitely the old masters that you want to kind of, you know, they're your sages, they're wise men. They're the top of the tier if you want to talk about Sega Master System, and they've been involved with a whole bunch of projects. So one of the bigger ones is the Phantasy Star retranslation one. That thing is amazing on itself. So, I mean, Phantasy Star was the game that really got me into the Sega Master System. So, and for me, living in America, every kid I knew on the block had a Nintendo, including myself. And I only knew like 5 kids or 5 people that actually had the Master System, but you know, I was heavily into it because of Phantasy Star. When I saw a commercial and they just had a little blurb of the dragon, one of the dragons on, I don't know if it was the Ice Dragon or the Cospa Dragon or whatever that dragon is. I forget which one it is, but they had it in the commercial. I was like, I gotta have this game. It was amazing. Phantasy Star, hands down, my favorite 8-bit game of all time. It will always be. So, all right, I jibber jabbered enough here, so I'm gonna leave off at this, and I think the next video will probably be my last. Even though there's a bunch of scenes that are in the game, the title screen that we're going to go over and the source code is very much like copy and paste for the rest of the other stuff. So the scenes and the title logic and stage logic, they kind of mimic each other with the substates. Very much the same thing. I don't think there's anything that is mind-blowing across them. We're just going to do the title screen to get it done so that we can apply the pack boost and we can show that off a little bit, and some of the other options that you can choose through the title screen that bleeds into the option screen. So we'll do that next video, and I think that will be the end of it, and it's been fun, so I'll see you next time.